Two things, really. It's great to be at the close to the end of the session because lots of things were introduced already and you can leverage those information. The downside of it is please don't fall asleep on me. So just stay awake. I'll try to be quick and make this interesting. So everybody was talking about the simulation. This presentation and my speech is really talking about the formal verification on the RISC-V and how to really ensure the compliance and trust to that RISC-V architecture. So before I jump into those details, I would like to give you a high-level overview of what OneSpin really provides and who we are. So first of all, OneSpin provides formal tools that we are selling. So we are an EDA company. And starting from the top left, we have the tools that provide functional verification. So the apps, automated checks, coverage, etc. Then what Mike was talking about, we also have functional safety verification. So when we are talking about the DO254 or ISO 26262, we have the analysis and diagnostic solutions that you can use. And finally, trust and the security. So everybody was talking about that at the end of the day. There, what we need to make sure that all the Trojans or anything that is added into our chip is really caught and that it is verified that it is really intended to be there, but not that it is a Trojan or anything like that. Some of the hot applications where our tools have been used is really heterogeneous computing, where you have huge SoCs with the AI, 5G, all the popular topics. So that's where companies are using our solutions. Then the RISC-V, that's what I will go into the details. So thank you, Larry, for the introduction. So I'll skip some of my slides. And finally, the automotive and the industrial. That's really where if you have a fault in your design, you want to make sure that your safety mechanism is catching it. And then you need to do the diagnostic and meet some AC levels if we are talking about 26.2. So Mike gave a really good overview of all that. So thank you, Mike, for that. So just a few words on top of what Larry said. Really, RISC-V is a free and open platform that came initially from Berkeley, California. So one thing, it is a very complex platform, but the nice thing about it, it is flexible. So we can add our own instructions. And that way, it is really flexible in a sense that users have capabilities of doing stuff. Now, on the other side, yes, it is free, but the problem with being free is really that everybody can interpret the ISA on its own way. So we need to do a thorough verification of such a design. So I will not spend too much time on this slide because previous presentation mentioned all of them. So there are many challenges that we need to address as part of the design and later on during the verification. First of all, the compliance. Really, the RISC architecture is developed initially by Alan Turing, I would say, so quite old. So every next generation of it needs to really be compliant. Then also, since it is an architecture with a core, we need to address the safety and security and the trust on it. And also, as said, there is already a part of the verification environment that is there. So some of the requirements, and I will mainly talk about the formal-based approach and the requirements that can be addressed with formal. The big advantage of the formal, as we all know, it provides us the full proof. So when the formal tool says something is proven, then it really means that if we are looking from the simulation perspective of view, that there is no trace to violate that statement. So really solid. What is the idea? In general about the verification, it's really hard because there are so many operations that are already there and users can add their own. That's why formal is really good to cover all those aspects. And then I will talk about that in the next slide. Formal also allows, using the technology and the methodology that we really provide, is catching anything else that may exist in our design. So not only verifying the core functionality, but also verifying if there is anything else. That way it can be also addressing the trust and the security and the safety part of it. So when we've been developing the solution, we had to address few challenges. Obviously, we all know that formal can suffer of the bounded proofs if it gets to the complexity. And since many different implementations of it exist today, we had to address the reusability. So that if Jim wants to, probably he won't, but if Jim wants to verify his own RISC-V, and Dave as well, they can develop it differently, so we need to be open. I'm just, because you have your own tools. You don't need OneSpin, right? Okay, so, yeah, you're with him, right? Yeah, okay, so what we use there, so we based the solution on the standard system Verilog approach. So again, which allows us the compliance to the ISA. And also, it also provides us the capabilities, as I've mentioned already, to really verify any additional functionality that can be there. So what we as users will have to do is to provide the tool with the information of the design configuration. So for example, if we have 1 or 5 pipeline stages, so it's really not plug and play. So there is certain inputs, but it is just the configuration part of it. How am I standing? You're good. Okay, good. And yeah, how did we get there? So this is really a unique OneSpin technology, and I would also say the methodology. It's called gap-free verification. So when I say the technology, the tool guides you to do the verification. So I could even say the tool forces you. And then talking of the methodology, what this approach allows you to do is to create assertions on the higher level. Those are called operations. So let me maybe give an example. Say that we have a simple FIFO, and then you write read and write operation. So what you can use this technology is really to verify if these operations are complete. And then the tool will say, well, I'm sorry, sir, but you didn't specify what happens if there is no write and there is no read request. And that's something that the tool will give you in a waveform. And that way, the safety aspect and security aspect is also addressed. So if you have added an operation or someone else has added operation, then the tool will catch that and it will flag it. Hey, is this something that you intended or not? So that's way you can get the full proof and 100% functional coverage on your RISC-V implementation. So how is this work created? So again, we try to address one of the requirements that I mentioned in the earlier slides, which was really to make it portable to other solutions, to other implementations, I'm sorry. And then while creating it, we used several examples of the cores. One of those is Pulpino SoC that can be found at GitHub. Since this is a very recent work, we had a press release that last DVCon. We'll be talking next week at GOMAC in Albuquerque, New Mexico, I'm sorry. And of course, during DAC in Las Vegas. So what we did, let me tell you just a few words about this platform. So it's a single core platform, but it is very rich with peripherals. And all the details about it can be found, and that's where we downloaded it from the GitHub. So what is a big advantage that we try to use from the tool is not only create this solution, but since there are many added features that are not part of the ISA, we used one of the standard apps that come with the tool. So automated checks, verification IP, floating point unit, and many others, which we use really for the verification. And then later on, we've been adding these operational assertions using the gap-free to verify the core functionality of the SoC itself and and according to the standard. And one last slide is really probably the most important. So what did you find, right? While running and creating all this verification environment, our floating point unit verification app has found a corner case where adding 2 negative zeros is actually producing positive 0. So instead of being minus 0, it was plus 0. And this was confirmed already by Pulp team to be a bug, and it's being fixed. Another one is using one of our auto checks. So what has happened there was a piece of code that had a parallel case, and the tool has found that at the same time 2 branches of that case can be activated. Also being confirmed. And finally, one last one that you also see, we wanted to give you an idea of the waveform. Our APB interface checker, so if I go back here, there is an APB that talks to all these peripherals, has found that there is inconsistency to what the AMBA standard states. So this is something that has been analyzed. So there are a few other cores that we've been running this solution on. I can't list them, but there are also bugs that have been reported. And we are still waiting to hear back whether there are issues or not. So whether we need to add a certain configuration to the solution itself.